Sound check, sound check. AP Chemistry, this is the answers video for the Princeton guide questions that we did. We did them a week ago. We're doing them again today. Remember that you have the answers to these. They're in the Princeton guide, but I'm going to go over and give you some explanations that might be helpful and some tips. One of the things you want to do is learn to do these problems, not only be able to do them, but do them as quickly as possible, okay? So let's go ahead and do this. So multi-step reaction. So these are elementary steps. With the following elementary steps, what is the overall balanced equation? So this is the third part of Hess's law where you can add and subtract. So what you do is you find something that you just pick one and you see what should it be doing in the overall reaction. So I'm going to start with N2O2. It's a product on step 1 and a reactant in step 2. So that makes it an intermediate. So that means it's going to cancel out. It should not, I don't see N2O2 anywhere else, so it's going to cancel out, so it should not be in the final overall reaction. So when I look at A, I see N2O2. It shouldn't be there because it cancels out. If I look at B, I don't see it there. If I look at C, I see it right there, so that one's eliminated. It can't be it. D, I don't see it. So it's down to B and D. All right, let's go to another one. How about H2? Okay, you can pick a lot of different things. It doesn't matter the order. H2 plus H2 is 2H2. And there's no other H2s. They're both on the left side, so it's H2 plus H2 is 2H2. So the final answer should have 2H2 on the left side. I look at this one, B, it doesn't have 2H2, so that's eliminated. So don't just assume it's D because that's the only one left. Let's check. It does have 2H2. It has 2NO. Now there's a 2NO there, and it's nowhere else in the reactions. So yes, it needs to show up on the left. And then let's see, what else do we have? We have an N2 on the right side of this arrow. You don't see N2 anywhere else, so it should show up, and it does. And then finally you have H2O plus H2O is 2H2O. So D is the correct answer, okay? Always verify that answer is correct. You might have made a mistake somewhere else. Okay, next. We have, what is the role of N2O2 in the overall reaction? And I just said that it's an intermediate. It's produced in step 1, it's consumed in step 2, doesn't appear anywhere else, so that's going to be B. All right? If step 2 is the slow step, what is the rate law for the overall reaction? Okay, so remember, if the slow step is somewhere other than the first step, you're going to have possibly a complication because this step, so let's write it down, this is the slow step, is going to hold up the overall reaction. Okay, so they're saying if step 2 is a slow step, what's the rate law? So we know that the rate law is of the overall reaction is the rate law of the slow step. So let's write it over here, what that would be. Okay, and for the slow step, it's going to be, you have N2O2 and H2. There's no coefficients, so it's simply going to be written like this. To the first power, I won't write that. And H2. To the first power, I won't write that. Okay, so now let's look at the overall reaction. The overall reaction can only have reactants. The only reactants that are going to be in the overall rate law are the ones that are actually in the overall reaction. So H2 is there, and it's there. But N2O2 is not there. So you cannot use this in the overall reaction. So what do? You substitute. So where do you find an equivalent for N2O2? You come up here. So it's N2O2 is equal to 2NO. So if we come down here, take that down here, and how would we write 2NO in a rate law? It would be NO raised to the second power because that is 2. So that becomes this. Okay, so this becomes this. So now you can just rewrite it. Again, on a test, you don't have to do all this writing. I'm doing it to demonstrate it to you. But on a test, you'd want to just look at it and say, okay, I see what it is over there, and move on to the next question. Okay, so is this one of the answers? And it is right there. It's B. All right, okay, next one. Again, if that's the trickiest one, and if it's still giving you problems, come talk to me and we'll practice a few of them, okay? All right, why would increasing the temperature make the reaction rate go up? Okay, that's the easiest question in the whole test here, okay? Various molecules in the reaction will move faster and collide more often. Boom, that's it, okay? Increased temperature increases the speed of the molecules. It increases the kinetic energy, which when they hit each other, they're going to break apart faster and speed up the reaction. Okay, let's move on to number 5. This is probably the most complicated one. This is the one that I told you that you didn't have enough information to do this when we did this last time. So let's read this. At 600 K, so let me stop right there. Usually when they give you a temperature, all they're saying is that the temperature is going to remain constant, which means the rate constant is going to remain constant. You don't need to plug the 600K into any equation or any part of this. It's just telling you it's at a constant temperature. They could have just as easily said that, at a constant temperature. Okay, so you have SO2Cl2 will decompose to form sulfur dioxide and chlorine gas right there via the above equation. If the reaction is found to be first order overall, which of the following will cause an increase in the half-life of this in breaking down? So this, you got to think carefully about this. If the half-life increases, if this breaks down at a half-life, let's say, of half of it every hour, just to give a simple number, and then another half at an hour. If the half-life increases, it means it's breaking down slower. Think about that. So the half-life goes from an hour for half of this to break down to 2 hours. So you increase the half-life. That means that this reaction is going from left to right slower. So increasing half-life. Okay, so increasing the half-life makes the reaction go slower. It takes more time for this to break down, and that's a slower reaction. Okay, so which of these will make the reaction go slower? Increasing the initial concentration of SO2. So you've now learned from Le Chatelier's principle that if you increase the concentration of this at the beginning, you make the room on the left side more crowded, and so it's going to want to go to the right faster. So it cannot be A. Increasing the temperature at which the reaction occurs. If you increase the temperature, and we're assuming that most reactions go faster with increased temperature, then that's going to speed up the speed to the right, not slow it down. We're looking for one of these that's going to make it go slower. So we're going to eliminate B. C, decreasing the overall pressure in the container. That's the tricky one. That's one that we talked about. What does pressure do to Le Chatelier's principle? So if you decrease the pressure, it wants to increase the pressure. Let me write that down right here. Okay, let's go over this. If you decrease, we learned this about the effect of pressure on a reaction. Okay, let me see if I can get the light on this. So if you decrease the pressure, you did that. How did you do that? You could have expanded the volume of the container. The reaction wants to return to its equilibrium by increasing the pressure. Now, at the time we did this sheet last week, you hadn't learned about equilibrium, about Le Chatelier's principle. So you didn't know this concept. Now, a reaction can increase the pressure by creating more particles, because by the equation PV, I'm trying to find a place to write this, PV equals nRT. If n goes up, if you increase the number of molecules or particles, then P will go up. And that's what the reaction wants to do to get back into equilibrium. So in which direction does it move to increase more particles? Well, on this side, it has 1 particle, or 1 mole. On this side, it has 1 mole, 2 moles. It has a total of 2. So it can increase the number of particles by moving quicker in this direction. So it goes from 1 mole to 2 moles right there. So that means it would decrease the half-life. The reaction going faster means it takes less time for this to break down, to get cut in half. And so therefore, by decreasing the pressure, you are going to cause the reaction to want to increase the pressure by creating 2 moles for every 1 mole that it gives up. And by doing that, you decrease the half-life. You make the reaction run faster. All right, so that's the answer C is not correct. So the answer is D. None of these will increase the half-life. Again, that's the situation that's the more complicated one. All right, so we can practice that if you still have some challenges on that. Okay, next question. So you have a generic reaction here, A plus B produces C plus D, and there's the rate law for that particular reaction. So what are the potential units for the rate constant for the above reaction? So I guarantee they're going to ask you one of those on the AP. Okay, so what you do is, first of all, let's understand what this is. So this reaction, A, is a first order reactant. Okay, so the exponent is what determines the order. A has got an exponent of 1, so it's first order. B has an exponent of 2, so it's second order. And you add those two together, 1 plus 2, that gives you the order of the overall reaction, so it's a third order reaction. So let's come over here and let's write the units for a rate are always, these never change. Molarity per second. It's how much you're using up, you're consuming your reactant solution per second. Okay, that's going to equal K times, so A is molarity, and B is molarity squared. It's molarity times molarity. That's what the square does. So it's times M squared, but I'd rather write that like this, times M times M. All right, so we need to get K by itself to find out the units of measure. So we're going to divide this side by M times M times M, and they cancel. And over on this side, we got to do the same thing, divide by M times M times M. Just create some space for myself here. Okay, so there you go. So K equals this. Now you can cancel one of the M's with one of the M's here, or cancel the M on the top with one of the M's on the bottom. Okay, so I'm going to move over here where I have some space. So what you end up for the units for K is you cancel the M on top, so you have a 1 there now. And then you have M times S on the bottom. And now we're going to call the M times M, M squared. Okay, so that's your final units. But they don't present that as an option here. So you have to understand how exponents work. If an exponent is a positive number in the denominator, you can move it up to the numerator and change it to a negative sign. That's just math. That's not chemistry. Same with this one. This is S to the first power. I can write it like that. So if I move that up to the top, it becomes S to the negative first power. So this is going to be M to the negative 2 times S to the negative 1. That's what this is equal. Okay, and so your answer over here is this one right here, C. Okay? All right, so you got to practice those because I'm going to give one to you, guaranteed. Okay, this problem is similar to the earlier one. The following mechanism is proposed for a reaction. So you have a fast equilibrium step, you have a slow step. So the slow step's going to clog up the reaction. It's going to slow everything down. And then you have a fast step at the end. So we know that the rate determining step is the slow step. The reaction can't go any faster than its slowest step. So the question is, which of the following is the correct rate law for the complete reaction? So this is a good chance to practice the earlier problem again. So the rate law for the overall reaction is the rate law for the slowest step. So what is that going to be? So rate equals K, and I'll just call that step 2. This is the second step, times C, and it has no coefficient, so it's to the first power, and B, and it has no coefficient, so this is also to the first power. Okay, there you go. That's the rate law for the overall. But we have the same problem we had in the earlier problem. So first thing you got to do, and really should have done this first, is figure out what the overall reaction is. So let's look at it. We got B on the right and B on the left. They cancel. We have 2A on the left and A on the left, so they add. So they become 3A. Okay, so I'm going to circle them because I used them. We have D on the right and D on the left, so they cancel. And we have C on the left and nowhere else, so it's going to be 3A plus C. And then, so we use that one. And then we have E, and it's on the right side, and it doesn't cancel or add, so it's going to be E. So this is 3A plus C equals E. Okay, so the only reactants that can be in the overall rate law are A and C. So we have a C there, but we have a B. So just like the last problem, we have to substitute out the B. So how do we do that? Well, if we come back up here, I kind of scratched over it. Let me rewrite this top reaction. Again, we can treat this arrow like an equal sign. So B equals 2A. So this B is going to be equal to 2A. And when we write that in the form of a rate law, it's going to be A squared. The coefficient becomes the exponent. Okay? So now that means we take this reaction, we're going to bring it over here. It's going to be rate equals K, C, and the B is going to turn into A squared. So that's our final rate law for the overall reaction, and the answer is this one right here, B, C squared. B, rate equals K, C, A squared. Okay, what I got right there. All right? Okay. All right, let's read this. The reaction above takes place with all the reactants and products in gaseous phase. Which of the following is true of the relative rates of disappearance of reactants and appearance of products? That word relative just means if I have 2 moles here, 2 moles disappear here, 2 moles will appear here. If I have 200 moles here, 200 moles will be here. If I have 42 moles here, 42 moles will appear. It's just, that's what relative means. It means it's just a relationship, not a specific number necessarily. Okay. All right. So so let's see. So you're going to assume that all of these things happen in the same amount of time. They have to. So you're going to lose 2 moles of NaCl in, let's say, a minute. And then in that same minute, you're going to gain 2 moles of NO, and you only have a 1 for Cl2, so in that same minute, you're going to gain 1 mole of Cl2. All right, so let's read which of these. NO appears at twice the rate of that NOCl disappears. No, it doesn't. It appears at the same rate. You're going to end up with, after 1 minute, with 2 moles of this. If 2 moles of this disappears. So that's wrong. NO appears at the same rate that NOCl disappears. Okay, that is true. NO appears, you'll get 2 moles in 1 minute, and you'll lose 2 moles in 1 minute. So that appears to be the correct answer, but you should always read all the answers without wasting a lot of time. Check all the others. NO appears at half the rate that NOCl disappears. No, it doesn't. It appears at the same rate. In 1 minute, you lose 2 moles, you gain 2 moles. Okay? All right? so that's not correct. Cl appears at the same rate that NaCl disappears. No, you only get half as many moles of Cl as moles of NaCl disappeared. So if you lose 2 moles of this, you're going to gain 1 mole of this in a minute. So that's not the same rate. Okay, this only moves half as fast. So that's not correct. So the answer is B. Okay? Okay, let's go on number 9. When the reaction given above takes place in a sealed isothermal container. Isothermal, let's learn what that word means. It's not really important. Well, it is important, but it means same temperature. So again, in these kinetics reactions or problems, the temperature has to stay the same. Because if the temperature changes, the rate constant changes, and then everything, you can't do the problem, okay? Suddenly you got a changing rate constant. So same temperature, okay? That's what isothermal. Iso, same, thermal, temperature. Okay, so there's the rate law. Now, you didn't get the exponents of 1 and 1 because of the coefficients. Remember, in an overall reaction, you have to get this experimentally. Okay, so you can't just assume that those coefficients are that, okay? But anyway, there's the rate law. If a mole of H2 gas is added to the reaction chamber and the temperature remains constant, so that's important, which of the following will be true? The rate of the reaction and the rate constant will increase. Well, let's go ahead and write this out here. I'm going to write it out over here. Now, a lot of you, and you should be able to eventually do this kind of in your head. Not do all this writing. I'm doing it to explain it to you. Okay, so there's the same rate law. So let's just say they're 1. I'm just going to assign numbers to them. 1, 1, and 1. So it's 1 times 1 times 1, that it would equal a rate of 1. Now what they're saying is we're increasing H2. Let's just say we double it. Well, it says you added a mole, but let's say you go from 1 to 2. So now the concentration of I2 didn't change. The concentration, the K does not change. Changing the concentration does not change the K. So now it's 1 times 2 times 1, so that means the rate doubled. So it's first order, it's a first order reactant. You double the concentration, you double the rate. That's what we've talked about in the past, okay? So let's see which of these is true. The rate of the reaction and the rate constant will increase. Yes, the rate of the reaction will increase, but not the rate constant. It stays the same. You didn't change the temperature, so you didn't change the rate constant. So that's gone. The rate of the reaction and the rate constant the rate of the reaction and the rate constant will not change. Well, true, the rate constant will not change, but the rate of the reaction does change. It's saying both of those will not change. That's not true. Because the rate will change, it doubled. Okay, the rate of the reaction will increase, that's true, and the rate constant will decrease. Again, false. Nothing happens to the rate constant as long as you keep the temperature the same. So that's false. So D, the rate of the reaction will increase, that's true, and the rate constant will not change, that's true. So the answer to that one is D. All right, number 10. The above reaction will experience a rate increase by the addition of a catalyst. Which of the following explains why? So the reason I gave you in class when I taught you this is it lowers the activation energy. So if this is the products, this is the reactants here, and the products end up over here, then the energy diagram is going to go up. You have to put energy in, and then it comes down and reaches the products. Okay, so remember that. This is energy, and this is the time that the reaction takes to run. Okay, so the catalyst will cause the value for delta G to become more negative. You don't know what delta G is, and that's not the right answer anyway. You will learn what delta G is upcoming. Okay, the catalyst decreases the bond energy in the products. No, catalysts don't do anything to bond energies, all right? C, the catalyst introduces a new reaction mechanism to the reaction. That is the correct answer. That's not the definition I gave you. I told you that what it does is it makes this activation energy go down, okay? So that this reaction has less of a hill to climb over to get over and down to products, okay? Now the last one, the catalyst increases the activation energy. No, that's exactly the opposite. Remember, activation energy is bad. If you want the reaction to go forward, it's bad. Increasing would make that mountain that it has to climb over really high. So that's not a good thing if you increase the activation energy. So the answer is C. It introduces a new reaction mechanism for the reaction, okay? All right. Okay, let's do 11. All right, one of these again. So again, if you're going to determine the rate law for an overall reaction, you can't do it by using the coefficients on the equation. You have to do it experimentally. So you want to get to where you can get pretty good at doing these quickly in your head. So it says, based on the following experimental data, what is the rate law for the hypothetical reaction? So when I look over here, I don't like scientific notation. It freaks me out a little bit when I have to do numbers. Since they're all 10 to the minus 2, I'm just going to X them out. So you're just dealing with a 3, a 6, and a 6, okay? So remember what the technique for this is. You're going to hold A constant and see how changing B affects the rate of the reaction. So A is held constant in these right here, 1 and 2. It doesn't change, but B changes. It doubles. It goes from 0.1 to 0.2. And the rate doubles. It goes from 3 to 6. So the way you do it is you write the concentration, okay. All right, so we make a ratio of one number over the other. We're going to choose to put the 0.2 on top because it's bigger. So it's 0.2 over 0.1. That equals 2. So, and the rate went from 3 to 6, so we put 6 over 3. And that equals 2. So it's 2 to the x equals 2. So 2 raised to what power gives you 2? The answer is x equals 1. Okay? All right. So that means B is a first order. Okay? And so B is first order. Doesn't matter which one you call x and y. So it's going to be B to the first. Okay? Now we're going to come down here. We're going to hold B constant. So that would be equations or reactions 2 and 3. So if you hold B constant, then A doubles. It goes from 2 to 4, and the rate doesn't change. So you double the concentration of A, but the rate stayed the same. That's a 0th order. It means the rate is not affected by the concentration. So if we did it the way I just did that one above, so this one was for B. I did B first. In A, it would be full 0.4 over 0.2. You want to put the bigger one on top. Equals 2. And the rate is 6 over 6, which equals 1. So 2 to the y power equals 1. Well, any number except 0, any number raised to the y power is 1. Raised to the 0 power is 1. So that means y equals 0. That means that A is 0th order, is 0. Okay? So now if we write the rate law, it's going to look like this. Rate Okay, so this just becomes a 1. So 1 times anything is just itself, so you can get rid of it, okay? So it's going to be K concentration of B, and that's the answer. That's answer C right there, okay? But here's the thing. You want to get to where you can do this in your head pretty quickly. These are easy numbers. Okay, so real quickly, I see that you hold A constant, that these two that if you hold A, that these are going to double, the concentration doubles, the rate doubles. Automatically, that's first order. You want to develop that proficiency. So that means the exponent for B is going to be a 1. Now you come down here, you hold B constant. A doubles, the rate doesn't increase at all, doesn't change at all. So that's going to be 0th order, All right, and so you got a to the 0, b to the first, bam, you're done with the problem. The a to the 0 disappears, and it gives you that. Okay, that's when you want to practice these enough times to where you can do that in your head. They'll give you simple numbers, except for that wasn't a simple, but you just get rid of the x to the 10 to the negative 2. Okay. Okay, on to problem 12. A proposed reaction mechanism for the reaction of nitrogen dioxide, that right there, and ozone is detailed above. Which of the following is the rate law for the reaction? So remember, slow step first is easy. That's the one where you don't have the substitution complication. Slow step first. Okay, so slow step first is easy. And the rate law for the overall is going to be the rate law of the slow step. So it's going to involve NO2 and O3. They're both elementary steps, so you can use the coefficients. And so you're going to simply come down here and write rate equals K NO2 O3, and you're done. Okay, right here, this one right here. Okay, that was easy. The other two were harder because the slow step came later in the reaction mechanism. Okay, whoops. Okay, reactant A underwent a decomposition reaction, so it's breaking down. The concentration of A was measured periodically and recorded in the chart above. Based on the date of the chart, which of the following is the rate law for the reaction? So this is one that wants to see if you understand the concept that for a first order reaction, if you go through the half-life will be equal time intervals. So this is 1 hour from 0 to 1. From 1 to 2 is 1 hour. From 2 to 3 is 1 hour. And you see over here, it's getting cut in half for every one of those 1 hour time intervals. 0.4 to 0.2, it gets cut in half. 0.2 to 0.1, it gets cut in half. 0.1 to 0.05, it gets cut in half. So that means it's a first order reaction, and that means the answer is this one. It's a little smudge there, but rate equals K, concentration of A to the first power. That's first order. Okay, you never have coefficients in front of K like these two. And this would be second order. That would not have that pattern of equal time intervals, give you an additional half-life. All right, number 14. So here you have a reaction. You have a single reactant. Rate equals Ka squared, so that's a second order reactant and a second order reaction because you only have one reactant. Which of the following graphs may have been created using data gathered from the reaction? Okay, so this is where you need to memorize the slope. So for 0th order, it is a negative downward slope. The concentration does not, the rate does not change. Remember the slope, the negative of the slope equals negative of K. So let me say that again. The slope equals negative of K, or you could say K equals the negative of the slope. So it's a straight line. I know it looks like a curve. It's not. It's a straight line. So as the concentration goes down, it doesn't change the slope. That means the rate stays the same no matter whether you have a high concentration up here or low concentration down there. Next, first order. Looks like that. And if you linearize it, so again, this is the original concentration of A versus time. And with first order, if you take the natural log of the concentration against time, it gives you a negative slope like that. Okay? So again, K is the negative of the slope. Okay? Finally, second order. So this is first. Let me write that there. This is second. Okay, and it has a curve that looks somewhat like the first order. You can't really tell much difference. Okay, now let me draw this. And this one, if you plot 1 over the concentration of A versus time, you get a positive sloping line. So This is second order, so this would be the answer right there. Okay? You need to memorize these, all right? Okay. After 44 minutes, a sample of this, it doesn't matter what it is, some potassium isotope, is found to have decayed 25% of the original amount present. What is the half-life for K? So what they're saying is you start at 100%, so just write the number. Let's just say it's 100 grams. You start at 100%, and that's at time 0, so this is time, and this is the concentration. Let's say 1 hour later. Or no, let's not say 1 hour later. You can't say that. Okay, you're saying after one half-life, it's going to be to 50, and after a second, it's going to be to 25. So it's 2 half-lives. There's one half-life to get from 100 to 50, and a second to get from 50 to 25. And it says that it's going to be at 25 in 44 minutes. Okay? That's what it says. It says after 44 minutes, it's 25. Again, instead of using percent, I'm just using grams. Same thing. Okay, so then it's asking, what's the half-life? Well, what is one of these? Well, one of these is if that goes from 0, if it goes from there to there and there to there, and these numbers are going to be the same, it's going to go from 0 to 22. And then from 22 plus another 22 gets you to 44. So the half-life is 22 minutes. All right, here we got one that's got a little trap in it, similar to the one a couple problems back, except here I see something. It's 10 to the minus 3 versus 10 to the minus 2 versus 10 to the minus 2. So let's remember our rule for scientific notation. You have 5.0 times 10 to the minus 3. Now I need to get that to be 10 to the minus 2. That's one number bigger than 10 to the minus 3. So what I'm going to do is if I want to get this to go bigger to minus 2, I got to make this number smaller. So I'm going to move the decimal over to there. And so what we end up with is 0.5 times 10 to the negative second power. Now that I have them all in terms of 10 to the minus 2, I do what I did on the last problem. I just get rid of this and these two, all these guys. So now I'm simply dealing with, instead of 5, I'm dealing with 0.5. So 0.5. I hope you can read that. Let me write it over here. 0.5, and this is 1.5, and this is 4.5. Okay, that's all you need to know in terms of the patterns, okay? So I noticed something that this one is 3 times this, and this one is 9 times this, and 3 times that. I'm just kind of looking for some, patterns there. Okay, so let's do the same thing we did before. We're going to hold A constant and do B. So if A is constant in 1 and 2, then this is going to triple. It's going to go from 0.1. I'm not going to write all the stuff I did last time. You want to learn to do this in your head. It's going to go from 0.1 to 0.3, so that's tripling. And this triples. It goes from 0.5 to 1.5. So if this tripled, if tripling the concentration triples the rate, then that's first order. In other words, in first order, the rate goes up by the same number of times as the concentration. So that means B is first order. You notice I'm writing very little. You want to get to where you can do these like this. Now we'll hold B constant. So that would be equations 1 and 3, 0.1, 0.1. So what does A do? It goes from 0.2 to 0.6, so it also tripled. Okay? It also tripled, so 0.2 to 0.6. What did the rate do? It went from 0.5 to 4.5. That's 9 times. Okay? So if I say 3 to the x power equals 9, so that was the increase in concentration, that was the increase in rate, then x equals 2, so that's second order. So that means A is second order, okay? So it's A squared B to the first, and so that is going to be this one right here, D, okay? A squared B to the first, okay? That wraps up this video, and I will do tutoring before and after school tomorrow, okay, if you want to see this and or talk about this some more. All right, have a good day.